Okay, today we're going to move on in our energy unit and we're going to look at how heat is produced and how we measure it. This says do now, but this is actually going to be our last activity, so not do now. This is going to be after we go through this slide and you look at the PowerPoint and your reference table, and you are going to need your reference table, so you're going to want to take that out if you haven't already. And you're going to do the questions on energy sheet 4 on the test wizard. Okay, so let's go over here to the next slide and taking a look at what temperature and heat actually is. Temperature is the measure of the average kinetic energy of the particles in the air. That's what we're going to really use it for. It could be in any body of matter, it could be in an object. And what is kinetic energy? We just looked at it. That's the energy of motion. So here's the way you should think about it. I'll just make a little diagram down here. Think of all the molecules in the air, and they're moving around, moving around, moving around. And the faster they move, the more they start to collide. And the more they collide, the more friction, and the more friction, the more heat. And that's the relationship we have here. So the greater the average kinetic energy or motion of particles, that makes a higher temperature, which is a direct relationship. So that kind of explains what temperature is. Now, how do we measure temperature? We have 3 scales that we use here in the US and around the world. The one that we use is Fahrenheit. Then in science, and it's actually part of the metric system, so the rest of the world actually uses this, would be Celsius. And for science especially, very extreme temperatures, we use Kelvin. And anything that's at 0 Kelvin or above has heat. So how are we going to convert our temperatures? We're going to go to page 13 of the reference table. So I have page 13 handy on me. And take a look. Here is the temperature scale on page 13. And there are 3 columns on this scale. There's Fahrenheit on the left, Celsius in the middle, and Kelvin on the right. So the first thing I want to do is figure out how much each line is worth for each of these scales. So let's start with Fahrenheit. Fahrenheit, I'm just going to point here to 200. See that big line sticking out? And then here's 220. If I count the lines between 200 and 220, there are 10 lines to travel from 200 to 220. So we're climbing 20 degrees divided by 10 lines. So on this scale, Fahrenheit goes up 2 degrees per line. And I want you to mark that on your reference table. For Celsius, let's go here to 100 degrees Celsius. Here's 110. There are 10 lines to travel 10 degrees. Therefore, Celsius goes up 1 degree per line. Mark that on your reference table. And Kelvin, I'll go to 370. Here's 380. 10 lines to travel from 370 to 380. So it's also 1 degree per line. So take a look. I mean, really, the only one that doesn't go up by 1 degree per line is Fahrenheit. So here's what can happen. I mean, very simple question. Let's hope you get a question like this. Let's say they say, all right, you're at 80 degrees Celsius. 80 degrees Celsius. What is 80 degrees Celsius in Fahrenheit? So what I would do if I were you, I would take a straight edge, maybe another piece of paper, which I'll do right here. I'll line it up, and I could tell what 80 degrees Celsius is, both in Fahrenheit and Kelvin. Watch. I'm going to slide over 80 degrees Celsius, go right here, and it looks like I'm at this line right here. These are going up 2 degrees per line. You see that little line sticking out for Fahrenheit? That's the halfway point between 160 and 180. So this is 170, and we're right here. So it's 172, 174, 176 degrees Fahrenheit. So 80 degrees Celsius is 176 Fahrenheit. And then if I were just to slide over and figure out what it is in Kelvin, Kelvin's going up 1 degree per line. Looks like I'm ending up right about here. 351, 352, 353, maybe 354. Don't worry about being exact. You'll see when you get multiple choice questions to convert temperature, it's going to be pretty obvious which is the correct answer. So that's how you would convert temperatures. I'll give you one more example. Let's start with, let's move down the chart a little bit. And you know what? I'm going to go to a very important temperature. Look on the left-hand side of this chart, and if you do that, you see these dashed lines here? These dashed lines go over to the left, and it tells you what's happening at that temperature. And this is a mighty important temperature in earth science, 0 degrees Celsius. Why? Because that's the temperature at which water freezes. So in order to freeze something, you'd have to cool it off. So let's say I started at 20 degrees Celsius, and I put the water 20 degrees Celsius in the freezer. It's going to keep getting cooler and cooler and cooler and cooler until it hits 0, and that's when the water will change to ice. So conversely, by the way, let's say I started with ice, then I would be below 0 degrees Celsius, right? And I take my ice out of the freezer. If I took it out of the freezer and it started at negative 20 degrees Celsius, it's going to warm up out of the freezer. So now it's going to get warmer and warmer and warmer. And now when it hits 0 degrees Celsius, instead of freezing, we know that ice will melt. So this temperature, it doesn't say it on the reference table, but you might want to write it down. At the same temperature, ice melts. It just depends what you're starting with, water or ice. So here's the question though. I'm at 0 degrees Celsius. What is that in Fahrenheit? So I'm going to slide over. It looks like I'm right at that line right there. Remember, for Fahrenheit, it's going up 2 degrees per line. So here's 20, here's 40. Remember that line over here is the midway point, that's 30. And notice that water freezes or ice melts at 32 degrees Fahrenheit. So just think to the winter when we're praying for snow, because I know we all love snowstorms. That's the magic number we usually look for, 32 degrees Fahrenheit. If that's what it is outside, I would say about 75% of the time, maybe 80% of the time, the precipitation would fall as snow. And we all like a big snowstorm. You know I love one. All right, and then what is 0 degrees Celsius in Kelvin? This is a really important number to know too. And I'm going to slide over. This is going up 1 degree per line, so 273 Kelvin. One other important, very important temperature is 100 degrees Celsius. The reason is that's where water boils. And if I slide over 100 degrees Celsius in Fahrenheit is, well, this is 200, that's 220. There's the halfway point, 210, 212. 212 degrees Fahrenheit is where water boils. Very, very important to know, and that happens to be, on the other side, 373 Kelvin. And one other thing, degrees Celsius, degrees Fahrenheit. Notice we don't put degrees for Kelvin. It's just Kelvin, so that should just be 1 per line. Okay, so that's how we're going to work with temperature. One last thing I'm going to look at here is specific heat, and this is going to be extremely important. Specific heat, where are we going to find all measurements for specific heat? We're going to find it on page 1 of the reference table. And this is the definition of specific heat. It's the amount of heat needed to raise the temperature of 1 gram of material by 1 degree Celsius. That sounds very scientific, very confusing. What is this simply? This is really what specific heat is. It's the resistance a material puts up to being heated up or cooled off. In other words, how difficult it is to change the temperature of a substance. So if we were to look at page 1 of the reference table, I'm going to go right here, and you're going to look at this chart. This is going to become extremely important when we are looking at weather. And in fact, very soon. I'm going to explain a little bit more in a minute. So here are 1, 2, 3, 4, 5, 6, 7, 8, 9 materials. Liquid water on the top, lead on the bottom. These are the specific heats. And what you're looking for is how much how hard it is to change the temperature of each of these materials. And here's how you're going to know. The higher the specific heat, the tougher it is to change the temperature. And notice something. If I start down here with lead, I start at 0.13. Then it goes up to 0.38, 0.45. This is going in order. So what you probably want to do on your reference table, draw an arrow right up the side here. This is going to be the smallest specific heat, and this will be the largest specific heat. Oh, you can't see that, can you? All right. That is what you should do on your reference table. Now, knowing that, if I were to compare, let's just say I get a question, what is going to change temperature quicker? Dry air, we'll make that choice A, or granite. I think I said which one's going to change temperature quicker. So how are you going to figure that out? You're going to compare the specific heat of dry air to granite. And when you compare it, you can see granite has a lower specific heat. Because it has a lower specific heat, it's going to change temperature quicker. We could heat it up faster, we could cool it off faster. So the answer would be granite is easier to change the temperature of, or we could heat up faster or cool off quicker because its specific heat is lower than dry air. Take a look at liquid water, by the way. Liquid water is by far the toughest natural substance, naturally occurring substance on Earth to change the temperature of. I mean, think about trying to boil water when you're making pasta. You fill up the pot with water, you throw it on the stove. Well, you don't throw it, you actually put it nice and gently on the stove, add some heat, and then you kind of walk away from the stove for a little while because you know it's going to take a few minutes for that water to start to boil. It's got to hit 212 degrees Fahrenheit or 100 degrees Celsius, right? So water is very, very tough to change the temperature. And that's how you're going to use this chart. So what I did in your PowerPoint, normally this will be in your class notes and you'd have to fill it in. I tell you to use your reference table, fill it in, but I just basically copied this off the reference table. Those are the specific heats, and then I just asked which material will heat up or cool off the quickest out of these three, and it's pretty obvious. Lead has the lowest specific heat, so it's going to put up the least resistance for its temperature to change. That's the answer to that. Now, why is that important? Water is really important. When we get to weather, you're going to see, and I'm just going to go above here and just kind of show you why this is so important. Eventually, we're going to kind of look at this. Maybe we go to the beach. There's the water. And here is right next to it. We'll make this the land. And it's going to be a nice sunny day. And it's the summer. So let's think of the summer. Let's think to better times right now. And the question is, what's going to heat up faster, land or water? In this case, this is the ocean. The land will heat up much, much quicker because it has a much lower specific heat than water. So, think about the ocean. When you want to cool off during the summer, when you're at the beach, it's nice to take a nice dip and dive into the ocean, right? It might be 95 degrees over the land, let's say by 2 o'clock, but in the ocean, maybe it's only 70 degrees. And it's going to take months to heat this up, even like 5 degrees. So, that's going to be our explanation of specific heat very, very soon. All right, guys, so hopefully that helps you. And I want you to do the energy sheet on Test Wizard. I believe it said Energy on Earth, sheet 4. And you guys actually have a quiz tomorrow, which I'll tell you about in our post later. All right, have a good day and enjoy.